Unit 4 Chemistry, Chapter 12, Part 5, Mass Spectrometry. And it is spectrometry, not spectroscopy now, because we're no longer using part of the electromagnetic spectrum, but we're still making a spectrum. Okay? This is a useful technique which you will have looked at before when you looked at the relative abundance of different isotopes when you were first learning about mole theory. Okay? It's used to separate molecules based on their mass. Okay? And we can use it to find the structure of organic molecules because we can find out how different atoms are grouped. And we can also find the molar mass, which is very useful. It's got four main steps, as you can see. Ionization, acceleration, deflection, and detection. Okay? In ionization, which comes first, we put the sample into the mass spec as a gas. Okay? And it goes into an ionization chamber which is filled with high energy electrons which bang, 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 bang at your molecule. Okay? The energy of that electrons is huge, way bigger than ionization energy. Hopefully you remember ionization energy. It's the minimum energy required to remove a single electron from the outer shell of a molecule or an atom or whatever it is you're trying to move on. Okay? Because their energy is so high, what they're going to do is knock electrons out. Okay? So we're going to make positively charged ions, cations. And in some cases that's going to be unstable and fragment, but we'll come to that later. Once it's been ionized, fragments then move into the acceleration chamber. Okay? And in the acceleration chamber we put it in an electric field, and that will accelerate any particle that got charged. Anything that didn't is now useless to us. We're going to forget about it, but we've got a whole bunch that have become charged, and they're going to go through and be sped up. And it's very clever because it makes sure they all have the same kinetic energy. So that's not going to be a factor when we move to deflection. The deflection, therefore, only separates them based on the mass to charge ratio. Okay? Basically, it is easier to deflect something or bend something which is small and light than it is to deflect something which is big and heavy. Now, the charge is almost always 1. That's the most common charge by a long way. So essentially, we're separating them based on the mass. So we'll start with a low magnetic field, and that's going to bend my smallest molecules so they hit the detector. Okay, and we'll measure them, and then we'll increase it a bit, and measure the next biggest ones, and the next biggest and the next biggest until we've done each fragment in turn. Okay? If they have got a charge of 2, then they're going to be deflected with some lighter molecules, okay, but not at exactly the same point, but they'll only give us some very, very small peaks that we're not going to be too interested in our analysis. Then we're going to detect them. So they hit the detector, that makes a current, and that's proportional to the number of particles that we get there. So from that can give us a graph that tells us how many of each type of fragment we've got. Okay? One more thing. In the ionization chamber, okay, we have our molecule, in this case let's call it ethanoic acid, and that is going to get ionized to make this cation. And I know it's something that doesn't normally make a cation, that's okay. Just in this specific instance it is. And of course an electron, because we need a balanced equation. Sometimes it will go through just as is, which will be useful because this is our parent molecular ion, and that is going to tell us the molar mass of the molecule, which is a great useful piece of information. Probably the single most useful piece of information you're going to get from a mass spec. But sometimes this is going to be too unstable and break up. And it might break up, say, into a CH3 and a COOH. And one of them is going to have a charge because we only removed one electron. The other is going to have that unpaired electron, which we'd call a free radical, okay, and is represented by that little dot. Okay. Now, sometimes the free radical will go on the CH3 and the charge on the COOH, sometimes the other way around. Okay, it's a slightly random process, so we will see both fragments in there. Only charged ones can be accelerated, so only charged ones can be deflected and therefore detected. So in this case, this particle would be detected, this one wouldn't. But another time with a different molecule, they'd break up and this one would get the charge, so we're still going to detect both ultimately. This is the kind of thing we're going to see. Okay? M over Z is along here. Now remember the charge is almost always 1, so basically this is telling you the mass. Our peak, which is furthest to the right, is our parent molecular ion. That's the whole molecule, not fragmented. That's the molar mass. Okay. The other important peak to know is called the base peak. Okay. This here is our base peak. It's our most stable fragment, and that's why it occurs most often. And it has, by definition, a relative intensity of 100%, because everything else is saying how abundant is it compared to that. Okay, so this is 90% abundant compared to that. So if I got this 100 times, I'd get that 90 times. Okay, these ones are still useful because they tell us what different fragments we've got. Okay, we wouldn't look at it in isolation and go, okay, we'll look at that and I can figure out that that's ethanoic acid. That's not possible. But we'd have done some IR, so we'd know it's a carboxylic acid. We would have done some combustion analysis properly, so we know its its empirical formula. And now we know its molar mass as well, and maybe we'd have some detail from some NMR as well, and we'd piece all of that together to get our overall formula. Okay? So that's the kind of thing you're going to find that you're looking at. In some mass specs, we're going to see some additional lines that might be due to the presence of isotopes. So they're going to be really close to the normal one, the one that we're expecting, but just a little bit higher. So for instance, if we had chloroethane, it's almost certainly going to have carbon 12 and hydrogen 1 in it, although those do have other isotopes as well. But commonly, when we have a halogen, all the halogens have got common isotopes. So chlorine-35 is going to appear, okay? And that would give us a mass overcharge of 64. But if instead of that, we incorporated chlorine-37, then we're going to have a mass overcharge of 66. What we're not going to see, though, is a peak equivalent to the average atomic mass of chlorine at 35.5, because any individual fragment can either have chlorine-35 or chlorine-37. Okay, so we might see something like this. Okay, and here we can see that we get a couple of lines next to each other. So this would be our base peak, but this is another one which is close to it, and that's going to be due to the isotopic effect. Okay, and you can see the same down here. Now our parent molecular ion is not particularly common, but we can see this one which will be due to chlorine-35, and then 2 points higher, this one which is due to chlorine-37. Okay? These little mini peaks here, they're so tiny, they're likely to be due to incorporating other isotopes of carbon or hydrogen in there.